Okay, so this is an example of how to solve the one-dimensional partial differential heat equation by using Fourier series methods. In the end, I will plot the solution in MATLAB. Okay, so this question is actually out of the book Elementary Differential Equations with Boundary Value Problems by Edwards and Penny. So here's the heat equation. Okay. So we have this insulated rod. It's well insulated. It's very, very thin with a constant cross-sectional area, and it has a length of 5 centimeters. Now let's say that on either end of this rod there's these constant temperature reservoirs, like a big block of ice or something that's kept at 0 degrees Celsius, and the temperature of those reservoirs does not change. So when heat flows into the reservoirs, it just gets distributed, but overall the temperature of these reservoirs doesn't change. Okay. So now let's say that at t equals 0, we heat up this bar uniformly at 25 degrees. Okay. So it has this initial condition. So like I said before, it has the reservoirs at either end at 0 degrees, and it has a length of 5, so that gives us boundary conditions of when x is 0 and when x equals 5, our function is going to equal 0 along the edges. Okay. So like I said here, we're going to use k equals 0.1 as the thermal conductivity constant. So we end up having this. And what does the solution look like for this? Well, through the method of separation of variables, if you suppose u of x of t is a function that consists of and you work this out, you plug this into this differential equation, what you end up with is, for this case where the 0 boundary conditions, okay, where ultimately you're solving for these constants b of n, and to do so, that's where the Fourier series comes into play. So when you set t equal to 0 in this equation, and here k is 0.1 for us, this term goes to 1, okay, because e to the 0 is 1, and you end up with this, which is the Fourier Sine Series. Also, I plugged in L equals 5 here. Should have mentioned that before. Okay, so, but what's this here? When t equals 0, that's our initial condition. So that equals this right here. So now, in order to solve this problem, and to find values for b of n, we need to find the Fourier Sine Series of 25. Okay, so how do we do that? So first, I think what they call it is you have to make this periodic. Okay, so you have to extend it along the number line like this. Okay, so when you extend 25, you make it periodic with a period of equal to 2L, in this case 10, and you turn it into this piecewise function that's an even piecewise function. then you can solve for Bn by using this formula. So basically you're finding B for different values of n. So you turn this problem into solving this integral. So in our case, I'm just going to leave n as n. I'm going to plug in 25 for f of x, and then I'm going to plug in 5 for L. You have 2 over 5. Okay, so I'll go ahead and integrate this. Okay, where n equals 1, 2, 3, integers, all the counting numbers. Okay, but look at this right here. This term inside these brackets here goes away whenever cos of this equals 1, because 1 minus 1 plus 1 equals 0. Okay, so when does cos of this equal 1? Well, whenever n is even. When n is even, cos n even equals 0. So whenever n is even, this term goes to 0, and b of n vanishes. But when n is odd, the absolute value of cos of an odd number times pi equals 1. So this equals 50 over Okay, so I wanted to plot this solution in MATLAB, but it's not very practical and not actually possible to write down an infinite number of terms. So what I did was I calculated the first 4 terms. Okay, I plugged in when n equals 1, when n equals 3, when n equals 5, and when n equals 7. And I used the first 4 terms of this infinite series in MATLAB to plot the solution. So you'll see it's not perfect, but it's pretty good. It gives you a good sense of how the solution behaves. Actually, the only problem is at our initial condition. You'll see that it doesn't quite fit our initial condition perfectly. It's a little bit wavy. You'll see what I mean in a second. But here are the first 4 terms. Okay, so here are the first 4 terms. This one here is when n equals 1. This term here is when n equals 3. This is when n equals 5. This is n equals 7. So let me open up MATLAB, and we'll get an idea of how the solution behaves. Okay, so I'm going to use the mesh function to plot this 3D surface. Okay, u of x of t is a 3-dimensional surface. So first, I did this earlier. First, I'm going to let time vary from 0 to 100. I played around with this number earlier. Next, I need to define the length of the bar. The length of the bar is x goes from 0 to 5. Next, I needed to do the mesh grid function to make it to plot the points for MATLAB to calculate u of x of t. Okay, so there's the first 4 terms of our function u. So to graph it, all you have to do is call the mesh function and input the arguments. So this is okay. So what are we looking at here? So time is along this axis. The length of the rod is along this axis. So you can imagine like the rod is right here, and it extends over to that other corner. And then these colors and these this surface here is the temperature distribution on the rod here at t equals 0. So this is our initial temperature distribution. So remember, our initial condition was u of x of 0 equals 25 degrees. And I was able to represent 25 as a Fourier series, but I only used 4 terms when I plotted this in MATLAB here, so that's why you have this waviness here. If I was able to plot the infinite series, then you would see that this would come up to 25 and go straight across to 25, and then back down to 0, because we said that at the ends of the rod there's those temperature reservoirs which are at 0 degrees. So here it's at 0 degrees, goes up to roughly 25 degrees all the way across, and back down to 0 degrees again. So now, let's say you look at the center of the rod. So when you slide down the surface, you are a point on the rod. You are a point on the rod moving forward in time. Okay, so at t equals 0, your temperature is 25 degrees, our initial condition. But as temperature moves forward, as time moves forward, the temperature at that point in the middle of the rod decreases. And then eventually, all of the heat that's in the rod escapes through the ends into the reservoirs, and you can see that it eventually reaches a steady state of 0 degrees throughout the length of the rod. Okay, so thank you very much for watching, and there'll be more videos to come.